In 1975, stomach cancer was, it was the most common, deadliest neoplasm on the planet. I mean, it was an
Okay.
absolute titan of global mortality.
Right. It was everywhere.
Yeah, but today, if you look at the epidemiological curves in high-income nations, its incidence has just plummeted. It's been in this continuous dramatic decline for decades. And the most fascinating part about this, the cure wasn't some trillion-dollar pharmaceutical breakthrough.
No, it
It
wasn't.
wasn't like targeted immunotherapy or a novel surgical technique. It was the invention of the kitchen refrigerator.
It is a really profound historical fact, honestly. When populations stopped relying on, heavy salt and smoke to preserve their food over the winter, the physical and chemical trauma to the gastric mucosa just dropped precipitously.
Wow.
The environment changed, and so the disease faded.
Welcome in, everyone. Whether you are a medical student cramming for your board exams, a junior doctor trying to make sense of the pathology reports on the ward, or, a public health trainee looking at the macroscopic forces shaping global disease, you are in the right place. We are taking a conceptual deep dive into the source material today.
Yeah, specifically, we're exploring the frameworks laid out in Chapter 8.2 of the Oxford Textbook of Global Public Health.
And just to be clear, we are not going to just read you a textbook. This is a companion piece. We want to build the conceptual frameworks that make those really dense lists of oncogenes and risk factors actually make sense.
Right, because when you first start studying oncology or cancer epidemiology, it's incredibly easy to get lost in the microscopic details. You memorize the genetic mutations, you memorize the staging criteria, the TNM classification, but you kind of miss the forest for the trees.
You definitely do.
You lose sight of how a mutated cell interacts with the patient and, crucially, how that patient interacts with their environment.
Absolutely. So to anchor our entire discussion today, I want to introduce a metaphor. I want you to stop thinking of cancer as just a biological event, like a broken bone or a sudden bacterial infection.
Okay, so how should we think about it?
Instead, think of cancer as a rogue cellular state. Think about what a rebellion or a rogue state actually needs to thrive, expand, and take over.
I love that framing because it requires a very specific sequence of events to successfully secede from the host organism. First, you need corrupted internal communications.
Right.
In our cellular world, those are the genetic mutations that tell a cell to, well, stop listening to the body's central command.
And second, you have to disable the local security forces.
Yeah.
A rogue state can't survive if the police shut it down immediately, which means the cancer must develop the ability to evade the immune system, right?
Yeah.
And bypass its own programmed self-destruct mechanisms.
Exactly. And third, a rogue state needs established supply lines to feed its growing army. In oncology, that is angiogenesis, the literal building of new blood vessels to siphon off the host's nutrients and oxygen.
And here is the critical part, which I think bridges the gap between clinical medicine and global public health. A rogue state doesn't just happen in a vacuum.
No, it really doesn't.
It requires very specific microenvironmental and macroenvironmental conditions to turn from a small, localized uprising into a full-blown systemic crisis. Yeah. The internal mutations are the seeds, but they absolutely require permissive soil to grow.
That's spot on. And our mission for this deep dive is to map exactly how that soil is tilled. We're going to trace the pathway from risk, which are the conditions that allow a hazard to exist, to exposure, which is how the hazard interacts with the human body.
Right. And then we'll look at how exposure drives cellular outcomes, and finally how public health interventions step in to alter the system-level impact.
To really understand the global epidemiology of cancer, the millions of cases, the staggering geographic disparities, we first have to look under the microscope. We have to understand the biological foundation of carcinogenesis before we can understand the public health response.
Let's ground this right away with a distinction that trips up a lot of trainees early on. The source material draws a very firm line between benign and malignant neoplasms. When we talk about a rogue state, we are talking about malignancy. But what is the functional behavioral difference between a benign growth and a malignant one?
Well, the functional difference fundamentally comes down to behavior, boundaries, and cellular identity. Benign neoplasms are localized growths.
Okay.
The cells have acquired abnormal characteristics. I mean, they're proliferating more than they should, but they largely maintain their normal tissue architecture. If you look at them under a microscope, a benign thyroid cell still looks remarkably like a thyroid cell. And crucially, they respect their borders. They stay put.
So, to use a clinical analogy for the wards, a benign tumor is kind of like a factory that lost its zoning permit and keeps building extensions on its own property.
Yeah, that's a good way to picture it.
It's annoying, it takes some space, and it can absolutely be dangerous if it's built right next to the city's main power line. Like a benign meningioma in the brain can press on the optic nerve and cause blindness.
Right, or a benign pheochromocytoma in the adrenal gland can pump out massive, unregulated amounts of adrenaline, causing life-threatening hypertension.
Exactly. It causes localized chaos, but the factory workers aren't, arming themselves, breaking down the fences, and marching to conquer the neighboring towns.
That captures the clinical reality perfectly. Malignant neoplasms, on the other hand, are defined by a sinister progressive growth accompanied by severe structural and functional alterations. As they mutate, they lose the identity of their tissue of origin, a process we call anaplasia.
So they forget who they are.
Exactly.
Yeah.
An undifferentiated malignant cell might not look anything like the lung or breast tissue it came from. But the absolute defining feature of a malignancy, the moment the factory workers militarize, so to speak, is the ability to invade nearby tissue.
They break through the basement membrane.
Yes. They break through, migrate through the lymphatic or circulatory systems, and colonize distant organs. That is metastasis.
Metastasis is the true hallmark of the rogue state. And to pull off that kind of systemic invasion, these cells have to acquire specific superpowers. Which brings us to a foundational concept in oncology. It's the widely accepted model by Hanahan and Weinberg, which outlines the 6 hallmarks of cancer.
Yeah, these are the 6 functional capabilities a cell must acquire to become fully malignant. These hallmarks are essentially the required curriculum for a rogue state.
Okay, let's walk through them.
First, the cells must acquire the ability to produce their own growth signals. Normal human cells are incredibly social. They wait for external instructions, growth factors, to tell them when to divide.
But malignant cells don't wait.
No, they bypass this completely. They often mutate oncogenes, which act like stuck accelerator pedals. The cell continuously tells itself to divide, totally independent of what the body actually needs.
So the first hallmark is basically infinite acceleration. They generate their own marching orders.
Exactly. Second, they must develop insensitivity to anti-growth signals. In a normal tissue environment, there are constant signals telling cells to stop growing, to maintain the architecture.
Like biological brakes.
Right. Internally, proteins like the retinoblastoma or RB protein act as the master brakes at the cell cycle checkpoint. They decide if a cell should proceed with division or enter a resting quiescent state. Malignant cells effectively cut those brake lines by mutating or deleting these tumor suppressor genes.
Infinite acceleration and now absolutely no brakes.
It's a bad combination. Third is the evasion of apoptosis or programmed cell death. This is the body's ultimate security mechanism.
The self-destruct button.
Yeah. When a normal cell detects severe, irreparable DNA damage within itself, a tumor suppressor protein called p53 steps in. p53 halts the cell cycle and triggers a cascade of enzymes that dismantle the cell from the inside out.
So the cell sacrifices itself for the good of the whole organism.
Precisely. But in the vast majority of human cancers, the p53 pathway is inactivated. The internal security guard is essentially tied up and locked in a closet.
Disabling the self-destruct sequence. That is terrifyingly efficient.
It really is. Fourth is immortalization, or limitless replicative potential. Normal cells have a strict limit on how many times they can divide, which is known as the Hayflick limit.
And that's tied to the telomeres, right?
Correct. It's dictated by the length of their telomeres, which are repetitive DNA sequences at the ends of chromosomes. You can think of telomeres like the plastic aglets on the ends of shoelaces. With every cellular division, those plastic caps get a little bit shorter.
And when they run out?
When they are completely worn away, the DNA begins to fray, and the cell permanently stops dividing.
But the rogue state needs to divide thousands, maybe millions of times to form a macroscopic tumor. How do they get around the shoelace problem?
They reactivate or overexpress an enzyme called telomerase. Telomerase's entire job is to constantly rebuild those plastic caps. By maintaining the length of their telomeres, malignant cells grant themselves biological immortality. They can divide indefinitely without ever triggering the senescence signals that stop normal aging cells.
Hallmark 4 is infinite lives. Which brings us to a major logistical problem for our rogue state, I would think. If you have a mass of millions of immortal, constantly dividing cells, they're going to run out of oxygen and glucose very quickly, right?
Oh, absolutely. A tumor can only grow to about 1 or 2 millimeters in diameter before the cells in the center start suffocating and starving,
So they need a supply chain.
which necessitates the fifth hallmark, sustained angiogenesis. To grow beyond that microscopic size, the tumor changes the local chemical balance. It secretes vascular endothelial growth factor, or VEGF, which signals the host's nearby blood vessels to sprout new capillary branches directly into the tumor bed.
Wow. So the rogue state just taps into the host's own logistics network.
Exactly, securing an endless supply of nutrients and an avenue for waste disposal.
And crucially, those newly built tumor blood vessels are often really leaky and poorly constructed, right? Which provides the perfect on-ramp for the final hallmark.
You're exactly right. The sixth hallmark is tissue invasion and metastasis. The cells alter their surface adhesion molecules so they can detach from their neighbors. They secrete enzymes called matrix metalloproteinases.
Molecular machetes.
I like that. Yes, they act like molecular machetes, dissolving the extracellular matrix and the basement membrane. This allows them to crawl into those leaky, newly formed blood vessels, travel through the systemic circulation, evade immune detection, and finally extravasate, exit the blood vessel to set up a new colony in a distant organ like the liver, brain, or bone.
When you lay out the 6 hallmarks like that, it sounds like an incredibly complex, highly coordinated achievement.
Right.
And here's where I have to push back a little, playing devil's advocate with the biology.
Go for it.
Human cells replicate billions of times a day. Every single time cell divides, it has to copy 3 billion base pairs of DNA. Mistakes happen. Typographical errors are totally inevitable. But if we are just rolling the biological dice billions of times a day, shouldn't these 6 distinct hallmarks emerge constantly by pure statistical chance? Like, shouldn't every human being be riddled with metastatic cancer by the time they are 10 years old?
That is the exact mathematical paradox that troubled early oncologists, and it gets to the very core of why cancer is predominantly a disease of aging. If carcinogenesis were just pure random chance waiting for one single normal cell to randomly acquire all 6 of those specific complex mutations in the exact right sequence, it would take significantly longer than a normal human lifespan.
So the math doesn't work out.
The math of random mutations simply does not support the incidence rates we actually see in the population.
So what is cheating the math? What is speeding up the clock on the rogue state?
2 fundamental accelerants: genomic instability and inflammation.
Let's start with genomic instability.
Genomic instability means the cell's sophisticated DNA repair mechanisms are fundamentally broken. We have dozens of proteins whose sole job is to proofread DNA during replication and fix the typos. If those proofreading mechanisms, like mismatch repair genes or homologous recombination genes like BRCA1, are mutated, the cell becomes a mutation factory.
It's like your typo correction software failing while you're typing at 100 words a minute.
Perfect analogy. Suddenly, mutations accumulate exponentially faster, drastically shortening the time needed to acquire the 6 hallmarks.
And the second accelerant, inflammation.
Inflammation, particularly chronic inflammation, creates a highly reactive microenvironment. Immune cells responding to chronic irritation release reactive oxygen species, which directly damage nearby DNA, driving that genomic instability we just talked about.
So it's actively causing damage.
Yes. Furthermore, inflammatory cells secrete growth factors, survival signals, and tissue remodeling enzymes. They inadvertently provide the exact soil the rogue seed needs. Chronic inflammation is the chaos that allows the rogue state to organize and expand.
This shifts our entire public health perspective. It means that carcinogenesis is not an overnight lightning strike. It is a long, multi-step process unfolding over years, sometimes decades.
Very true.
And because it is a long process requiring specific accelerants like genomic instability and inflammation, it creates a massive temporal window for us to intervene. But to intervene effectively, we first have to know what is causing the DNA damage and the chronic inflammation in the first place. Who is supplying the weapons to the rebellion?
Identifying the source of those weapons requires shifting from molecular biology to epidemiology. We have to identify the environmental and behavioral hazards that are initiating and promoting these cellular mutations.
Which brings us to the epidemiological toolkit used to track down these cellular criminals. And right away, we need to clarify a foundational conceptual framework that dictates public health policy. It's the critical difference between a hazard and a risk.
Oh, this is so important.
These terms are used interchangeably in the evening news, but in epidemiology, conflating them leads to disastrous misunderstandings.
The distinction is vital. A hazard is the intrinsic theoretical potential of an agent to cause harm. It is an inherent property of the substance itself, completely regardless of context. A great analogy is a great white shark swimming in the ocean. The shark is an absolute hazard. It has the intrinsic capability to cause severe harm.
Right.
Risk, however, is the statistical likelihood of that harm actually occurring to a specific individual or population. And risk is entirely 100% dependent on exposure.
So if you are standing on the beach looking at the water, the hazard of the shark exists, but your risk of being bitten is zero because there is no exposure. The moment you swim into the water, your exposure goes up, and therefore your risk elevates.
Precisely. When we talk about carcinogens, the first scientific task is simply to identify the hazards, to prove that a substance has the biological capability to cause cancer. The global authority tasked with this massive undertaking is the International Agency for Research on Cancer, or the IARC, which operates under the World Health Organization.
They act as the global intelligence agency tracking these agents.
Exactly. They evaluate all available global scientific evidence on a specific agent and categorize it into a classification system. This is essentially the global most wanted list for carcinogens.
Let's walk through how they structure this list.
The IARC classification system is the epidemiological gold standard. Group 1 is the definitive category. It means the agent is undeniably carcinogenic to humans.
So there's no doubt.
None. To get placed in Group 1, there must be sufficient evidence of carcinogenicity from human epidemiological studies. Causality has been established. As of the data referenced in our source material, there are 111 distinct agents in Group 1.
Group 1 is the smoking gun. We have caught them committing the crime in human populations. What about the next tier?
Then you have Group 2A, which means the agent is probably carcinogenic to humans. In this category, the evidence in human epidemiological studies is considered limited. Perhaps there is a strong association, but confounding factors can't be completely ruled out. However, there is sufficient evidence from highly controlled experimental animal studies.
To use a legal analogy, Group 2A means we have highly suspicious circumstantial evidence of the agent causing cancer in humans, but we actually caught the agent red-handed on high-definition video committing the exact crime in a laboratory rodent.
That is a highly accurate way to look at it.
We are fairly certain it's guilty, but the human jury is still deliberating a few details.
Following that is Group 2B, meaning the agent is possibly carcinogenic to humans. Here, the human evidence is considered inadequate or non-existent, but there is sufficient evidence of carcinogenicity in experimental animals.
A question that often arises from trainees and the public alike is, well, why do we rely so heavily on laboratory animal models and biochemical assays? I mean, we have over 8 billion human beings on the planet. Why can't we just look at the observational data for everything? Why do we need the rats?
We need experimental models because observational epidemiology, studying humans in their natural environment, has profound, sometimes insurmountable limitations.
We're messy.
Very. In the real world, human beings are incredibly messy subjects. We are exposed to tens of thousands of different chemical compounds every single day. We change our diets constantly. We move to different cities with different air qualities. We take varying medications. And frankly, our memories of what we were exposed to 20 years ago are deeply flawed.
This massive web of variables creates extreme epidemiological noise, otherwise known as confounding bias.
Exactly. If a specific chemical hazard only increases your relative risk of cancer by, say, 10 or 15%, observational epidemiology struggles mightily to confidently isolate that signal from the background noise of daily life.
Right, it gets lost.
As a general rule of thumb in epidemiology, any increased relative risk below 50% found in an observational study is very difficult to interpret definitively because the inherent unavoidable biases of observational methodologies are often of at least that magnitude.
That is a crucial, critical appraisal point for anyone reading medical literature. If a retrospective cohort study hits the headlines claiming that eating a specific type of berry increases your cancer risk by 12%, you have to look very critically at the methodology. The bias of recall or unmeasured confounding variables is likely larger than the finding itself.
Absolutely.
So to strip away the noise and isolate the variable, we move from the messy human world into the controlled laboratory.
We rely on 3 distinct types of experimental laboratory tests to build the case against a hazard. First, we use long-term, often lifetime, carcinogenicity tests in experimental animals, predominantly rodents.
What does that look like?
We expose them to a specific dose of the agent for their entire lives and observe tumor development compared to a control group. Second, we utilize short-term tests assessing DNA damage. These include mutagenicity assays, like the famous Ames test using bacteria, to see if the chemical directly alters the genetic code or causes chromosomal aberrations in cultured cells.
And third are the mechanistic tests. These are where we look under the biochemical hood. We try to map out the exact molecular pathway the agent takes to cause cancer. Does it bind directly to DNA? Does it generate those reactive oxygen species that cause inflammation? Does it mimic estrogen and act as a growth promoter?
When an agent consistently causes definitive DNA damage in short-term tests, reliably produces tumors in long-term rodent bioassays, and has a clear, mapped biochemical mechanism, it strongly supports classifying it as a hazard, even if the human epidemiological data is still messy.
But let's bring this framework back to clinical reality and public health policy. The IRC is building a global database of intrinsic hazards. But just because a chemical is sitting on the Group 1 Most Wanted list does not mean it is currently driving a public health crisis in your community. Because as we established, hazard must intersect with exposure to create risk.
That's the key.
Like plutonium is a definitive Group 1 carcinogen. It is incredibly hazardous. But your daily clinical risk of developing cancer from plutonium is functionally zero because your environmental exposure is zero.
Precisely. And that transition managing the space between hazard and exposure is where public health policy lives. We cannot eliminate every single carcinogenic hazard from the universe. Solar radiation is a hazard, but we can't turn off the sun. What we can do is regulate, legislate, engineer, and educate to minimize human exposure to those hazards.
So now that we understand how we identify the hazards, we need to look at the master criminals. We need to look at the agents that aren't just theoretical hazards locked in a lab, but are actively driving the massive global burden of disease, because human exposure to them is ubiquitous.
The scale of the global problem is staggering. According to the Globocan 2012 data referenced in the text, there were approximately 14 million new cases of cancer worldwide in a single year and 8.2 million deaths.
14 million new cases. And when public health experts look at this burden, they don't just count the number of deaths. That only tells a fraction of the story. They look at disability-adjusted life years, or dailies.
It's a much more comprehensive metric.
It's a brilliant metric because it combines two tragedies into one number. The years of life lost due to premature death, plus the years of healthy life lost due to disability while living with the disease and its treatments. The source material notes that lung cancer alone was responsible for an estimated 32.4 million dailies globally in a single year.
What is most illuminating about these massive global numbers is the extreme geographic variation in incidence. Cancer is not distributed equally across the human population. The textbook highlights the ratio between the highest incidence countries and the lowest incidence countries for specific cancers.
And some of those ratios are wild.
For malignant melanoma, the incidence varies by a mind-boggling factor of 405 between the highest and lowest regions.
A 405-fold difference. That is not a rounding error. That is not statistical noise.
Not at all. That massive geographic disparity screams that this is not just a random genetic event. It is an environmental exposure interacting with genetics. With melanoma, you have the environmental hazard of ultraviolet solar radiation intersecting with the genetic trait of cutaneous melanin production.
So fair skin and lots of sun.
Exactly. When you put light-skinned, low-melanin populations in high UV environments, like populations of European descent living in Australia, the incidence skyrockets compared to darker-skinned populations in the same area. Or light-skinned populations in low UV environments like Northern Europe, the environment shapes the epidemiology.
So if we pull back and look globally at these 14 million annual cases, what are the primary drivers? What are the macro-environmental conditions supplying the rogue cellular states? If we want to practice upstream engineering to prevent cancer before it starts, where do we target our policies? The text outlines 4 major exposure categories.
And number 1, unsurprisingly, is tobacco. Tobacco smoking is the single major cause of human cancer worldwide. It is a definitive Group 1 carcinogen that leaves a trail of genomic destruction.
Just absolute destruction.
In high-income countries, it is estimated to cause about 30% of all human cancers. And it is vital to note that tobacco does not just cause lung cancer. Because the carcinogens are absorbed into the bloodstream and excreted through various pathways, it drives cancers of the larynx, oral cavity, esophagus, stomach, liver, pancreas, kidney, bladder, and is even causally linked to myeloid leukemia.
The biochemical reality of a cigarette is terrifying. The text notes that mainstream cigarette smoke contains 81 known carcinogens, including 11 distinct Group 1 agents. You're inhaling polycyclic aromatic hydrocarbons and tobacco-specific nitrosamines that physically bind to your DNA.
They form bulky chemical adducts.
Right, which block replication and cause massive genomic instability. It is fundamentally a highly engineered delivery device for cellular chaos.
The second most important global factor might surprise many people, especially in high-income nations, and that is infectious agents. It is estimated that a substantial portion of the global cancer burden is driven by bugs. 9 infectious agents are currently classified as Group 1 carcinogens by the IRC.
This is where looking at the attributable fractions, or AF, is truly mind-blowing. The attributable fraction is the percentage of cases of a specific disease that can be directly causally attributed to a specific exposure.
For human papillomavirus, specifically the high-risk strains like HPV 16 and 18, the attributable fraction for cervical cancer is essentially 100%. HPV infection is a necessary biological cause for cervical cancer to develop.
100%. That's incredible.
For hepatitis B and hepatitis C viruses, the attributable fraction for liver cancer is 83.9% globally. For the bacterium Helicobacter pylori, the attributable fraction for non-cardia stomach cancer is 63.6%. And Epstein-Barr virus, or EBV, is strongly and causally linked to nasopharyngeal carcinoma and endemic Burkitt lymphoma.
Think about what that means conceptually. For a massive proportion of the global cancer burden, millions of deaths, the rogue cellular state is not initiated by an inherited mutation or a chemical toxin. It is initiated by an invading pathogen. The virus inserts its own DNA into the host cell's genome, directly disrupting oncogenes and tumor suppressors, or the pathogen causes decades of chronic inflammation as the immune system desperately tries to clear it.
This completely shifts the paradigm of oncology and prevention. We are no longer just telling people to avoid a chemical plume. We are talking about cancer prevention through the deployment of vaccines, like the HPV and HBV vaccines, and the use of basic antibiotics to eradicate H. pylori.
The third and fourth major global exposures categorized in the text are alcohol consumption and diet, which intricately includes the rising global threat of obesity.
Alcohol, specifically ethanol and its primary metabolite. Acetaldehyde is a Group 1 carcinogen. Acetaldehyde is highly toxic. It directly damages DNA and proteins, and alcohol metabolism generates reactive oxygen species.
And epidemiologically, what does that look like?
Epidemiologically, it increases the risk of oral, pharyngeal, esophageal, liver, colorectal, and female breast cancers.
And critically, alcohol does not act in isolation. It has a multiplicative synergistic effect when combined with smoking.
This is a vital mechanistic point. If smoking gives you a baseline relative risk of X for oral cancer, and heavy alcohol consumption gives you a relative risk of Y, engaging in both behaviors simultaneously does not result in a risk of X plus Y. It is X times Y.
It multiplies.
Yes. Alcohol acts as a solvent, physically dissolving the lipid membranes of the mucosal cells in the mouth and throat, allowing the potent tobacco carcinogens to penetrate much deeper into the tissue than they could on their own.
They work as a coordinated team to dismantle the local tissue defenses. And regarding diet, the epidemiological evidence remains complex due to the observational biases we discussed earlier, but clear patterns have emerged.
Definitely.
High intake of red and heavily processed meats increases the risk of colorectal cancer, likely due to heme iron causing lipid peroxidation and the presence of N-nitroso compounds. Furthermore, the textbook highlights the profound systemic impact of weight gain and obesity.
Yes. Adipose tissue is not just passive fat storage. It is a highly active endocrine organ. It continuously secretes excess estrogen, which acts as a growth promoter for breast and endometrial tissue, and it secretes adipokines that maintain a state of chronic, low-grade systemic inflammation.
It changes the whole metabolic environment.
Exactly. This metabolic environment is definitively linked to higher risks of postmenopausal breast, endometrial, renal, and colorectal cancers.
Having established these master risk factors, the pathogens, the toxins, the metabolic states, the crucial next step is to understand how these macroscopic exposures physically manifest in specific organ systems. How does the systemic soil dictate which specific rogue seed takes root?
Which means it is time to apply the frameworks we just built.
Yes, we're going to take the concept of the rogue cellular state, the hazard versus risk model, and the master exposures, and look at how they manifest clinically in major organs. We will follow the sequence laid out in the Oxford text. For the trainees and clinicians listening, this is where the abstract epidemiology transforms into the clinical pattern recognition you need on the wards.
Let's begin with the Titan lung cancer. As the data shows, it is the most frequent cancer globally, with over 1.8 million cases in 2012, and it remains the undisputed leading cause of cancer death.
When you look at the map, The highest rates are seen in Central and Eastern Europe and Eastern Asia for men, and North America and Northern Europe for women.
Those geographic rates are not a reflection of underlying genetics. They are a direct historical reflection of the tobacco industry's marketing success and regional smoking prevalence over the last several decades. Lung cancer is overwhelmingly a behavioral epidemic.
But what is fascinating is how human behavior has actually changed the microscopic pathology of the disease over time. The text notes a profound histological shift. Several decades ago, squamous cell carcinoma was the dominant histological subtype of lung cancer.
Right.
But in recent decades, particularly in the West, we've seen a massive shift towards adenocarcinomas. Why did the cancer change its shape?
It highlights how alterations in the hazard directly change the pathology. This shift is deeply associated with the introduction and widespread adoption of filtered, low-tar cigarettes. The filter vents diluted the smoke, making it less harsh on the throat. To achieve the same desired nicotine hit, smokers subconsciously changed their behavior. They began taking deeper, more prolonged inhalations.
They changed the aerodynamics of the exposure.
Exactly. The older unfiltered smoke was harsh and deposited larger particulate carcinogens in the central upper airways, which are lined with squamous cells, leading to squamous cell carcinomas.
I see.
But the deeper inhalation of filtered smoke drew the finer aerosolized carcinogens, particularly the tobacco-specific nitrosamines, deep into the peripheral alveoli of the lungs. The peripheral lung tissue is lined with glandular cells, and when those cells mutate, they form adenocarcinomas. The engineering of the cigarette changed the physical location and type of the resulting rogue state.
That is a staggering example of macroenvironmental engineering manifesting at the microenvironmental level. Now, when we look at the risk math of tobacco, we see an incredible dose-response relationship. The famous UK Million Women study referenced in the text demonstrated that the relative risk for lung cancer was 10.5 for women smoking 10 cigarettes a day and rocketed to 36.0 for those smoking 20 or more a day.
However, a core principle of cancer epidemiology is that while the daily dose matters, the dominant mathematical factor driving risk is the duration of the habit. The longer the lung tissue is continuously exposed to the inflammatory and mutagenic smoke, the exponentially higher the risk of multiple cells acquiring those 6 necessary hallmarks.
We will break down the specific math of that duration later, but I want to highlight the incredibly optimistic data the text provides regarding intervention. The human body's repair mechanisms are remarkably resilient if you simply stop poisoning them. The data shows that if a person stops smoking before the age of 40, they avoid more than 90% of the excess mortality caused by continuing to smoke.
That's a massive reduction.
The risk never goes perfectly back to baseline zero, but the catastrophic trajectory is aborted.
Which brings up the complex issue of screening for lung cancer. Can we catch the rogue state early enough to cure it? The textbook details the U.S. National Lung Cancer Screening Trial, the NLST. This massive trial demonstrated a 20% reduction in lung cancer mortality when high-risk individuals were screened annually with low-dose computed tomography or low-dose CT scans compared to standard chest X-rays.
But here is the profound clinical and ethical dilemma I want to pose, which the text explicitly notes. An annual low-dose CT scan exposes the patient to ionizing radiation. Ionizing radiation is a group 1 carcinogen. It physically breaks DNA strands. The text states that this annual screening regimen is associated with an estimated 5.5% increased risk of actually developing lung cancer from the radiation of the scan itself. How does public health balance this? We are utilizing a known group 1 carcinogen to look for cancer.
This represents the razor's edge of risk-benefit analysis in public health and clinical medicine. You are constantly weighing competing probabilities. You are comparing the immediate, tangible benefit of detecting an already existing, highly lethal rogue state at an early, curable stage against the delayed statistical risk of initiating a brand new rogue state through the cumulative radiation damage of the screening tool itself.
So how do you make the call?
You only implement this screening protocol if the specific population being screened has a baseline risk of lung cancer that is extraordinarily high. The NLST criteria focused on heavy, long-term smokers, people with a 30-pack year history.
Okay, so a very specific group.
Yes. In that specific population, the statistical likelihood that they already have an undetected growing tumor is so massive that the life-saving benefit of early detection mathematically dwarfs the 5.5% radiation-induced risk. Conversely, you would never recommend an annual screening CT for a non-smoker because their baseline risk of having lung cancer is so low that the radiation from the machine would cause more cancers than it would ever find. The harm would outweigh the benefit.
That perfectly illustrates why we don't just screen everyone for everything. Let's transition from the lungs to the liver. Hepatocellular carcinoma, or HCC, is the dominant form of primary liver cancer. And the epidemiology here tells a compelling story of viral and toxic convergence.
It really does.
The global burden is heavily concentrated in low-income regions. A staggering 83% of cases occur in developing countries, with 50% of the entire global burden located in China alone. Why is the liver so vulnerable in these specific regions?
It is driven by what we can call the dual hit phenomenon. In these high-incidence geographic areas, you have a massive population prevalence of chronic hepatitis B and hepatitis C viral infections. These viruses are often acquired perinatally from mother to child during birth or in early childhood.
Do they have it for life?
Exactly. The virus establishes a chronic infection, leading to decades of continuous liver cell destruction, regeneration, and severe inflammation. This chronic hepatitis and subsequent cirrhosis provide the ultimate accelerant for the rogue state.
But the virus alone doesn't explain the massive regional spikes. You need the second hit. You need the dietary hazard aflatoxin B1.
Correct. Aflatoxin is an incredibly potent, naturally occurring mycotoxin produced by Aspergillus fungi. These fungi readily grow on improperly stored agricultural crops, particularly corn, maize, and peanuts, in warm, humid climates lacking modern silo infrastructure.
So the local population is consuming this invisible toxin daily in their staple foods. How does it work biochemically?
Aflatoxin B1 is metabolized by the liver into an extremely reactive intermediate that physically binds to DNA. Crucially, it has a highly specific mutagenic signature. It specifically causes a mutation at codon 249 of the p53 tumor suppressor gene. It directly assassinates the cell's primary security guard.
Wow. So you have the hepatitis virus causing chronic liver damage, rapid cellular turnover, and inflammation, creating a chaotic environment. And simultaneously, the dietary aflatoxin is directly mutating the p53 gene, removing the brakes.
Yep.
The interaction between the viral infection and the chemical toxin is not additive. It is deeply synergistic. They multiply the risk exponentially.
However, the textbook highlights a critical pattern shift that all clinicians and public health trainees need to monitor. In high-income Western nations, North America, Northern Europe, Australia, we do not have high endemic rates of hepatitis B, and our food supply chain is rigorously screened to eliminate aflatoxin exposure. Yet the incidence of hepatocellular carcinoma in these regions is steadily rising. Why?
The soil is changing. It is the rise of non-alcoholic fatty liver disease, or NAFL, which is intrinsically driven by the compounding epidemics of obesity, insulin resistance, and type 2 diabetes.
Exactly. The excess adipose tissue and insulin resistance lead to the accumulation of toxic lipids within the liver cell's lipotoxicity. This NAFLD can progress to a severe inflammatory state known as non-alcoholic steatohepatitis, or NASH. The chronic inflammation and cellular stress mirror the damage caused by a virus.
And the text makes a profound clinical point here. While viral HCC almost always develops in a liver that has already progressed to severe cirrhosis, meaning it is heavily scarred. NAFLD and metabolic syndrome can drive the development of liver cancer even in the absence of cirrhosis.
That's a huge shift.
You do not always need the liver to be completely fibrotic and destroyed to develop a rogue state if the metabolic, hormonal, and inflammatory conditions are perfectly aligned to support tumor growth.
It represents a fundamental shift in the etiology of the disease in the West. But let's look at a tremendous public health victory outlined in the text to see how we can fight back. The Kedong region in China historically suffered from some of the highest HCC mortality rates in the world due to that viral and fungal dual hit. What intervention did they deploy?
They executed a masterful, coordinated, two-pronged primary prevention strategy. First, they implemented a rigorous universal hepatitis B vaccination program for all infants, effectively immunizing the next generation and cutting off the viral accelerant entirely.
Brilliant.
Second, and simultaneously, they completely overhauled their agricultural infrastructure. They improved crop drying and storage techniques and shifted dietary reliance away from susceptible maize towards rice, drastically reducing dietary exposure to aflatoxins.
The result was one of the great triumphs of modern epidemiology. By removing both the viral and the chemical drivers, they observed a dramatic, sustained reduction in the incidence of liver cancer in young adults. It is absolute proof that macro-level upstream engineering can eliminate a microscopic rogue state.
While the liver battles viral invaders and fungal toxins further up the digestive tract, the stomach tells a completely different epidemiological story. I mentioned it in the introduction. I call it the epidemiological miracle.
It really is a miracle.
In 1975, stomach cancer was the most common neoplasm in the world. Today, while it still causes a massive global burden, over 700,000 deaths in 2012, primarily in Eastern Asia, South America, and Eastern Europe, its incidence in high-income countries has been falling steadily for a century.
The dramatic, unprompted decline of stomach cancer in the West prior to the invention of modern oncology is a testament to the supreme power of environmental influence over biology. The primary driver of the decline was better food conservation, specifically the widespread adoption of the electric refrigerator.
How does a refrigerator prevent cancer?
Before refrigeration, populations had to rely heavily on massive amounts of salt, pickling, and smoking to preserve meats and vegetables through the winter. High concentrations of dietary salt act as a severe mechanical and chemical abrasive to the delicate mucosal lining of the stomach.
It just wears it down.
It physically damages the protective mucus layer, causing chronic gastritis, inflammation, and increasing the risk of cellular mutation twofold. The refrigerator allowed for the year-round consumption of fresh foods, instantly eliminating that daily, massive chemical trauma to the stomach lining.
We literally chilled the rogue state into submission by changing how we store food. But the story of stomach cancer isn't just about salt. There's a microscopic biological player that changed everything we thought we knew about gastroenterology, the bacterium Helicobacter pylori.
H. pylori was a revolutionary discovery. For decades, the medical establishment believed the stomach was entirely sterile due to its extreme acidity. But H. pylori evolved a biochemical trick. It secretes an enzyme called urease, which neutralizes the stomach acid in its immediate vicinity, allowing it to burrow into the protective mucus layer and colonize the stomach lining.
And the textbook notes that this chronic bacterial infection is fundamentally a necessary precursor for the vast majority of non-cardia stomach cancers in the main body of the stomach.
Yes, the presence of H. pylori drives a very specific prolonged pathogenic sequence known as the chorea cascade. It starts with chronic superficial gastritis, driven by the immune system's futile attempt to clear the bacteria.
Okay, and then...
Over years, this chronic inflammation leads to gastric atrophy, the loss of the normal acid-secreting glands. The tissue then undergoes intestinal metaplasia, shape-shifting to look like the intestines in a desperate bid to survive the inflammatory environment. This metaplastic tissue eventually develops dysplasia, accumulating mutations until it becomes a full-blown invasive adenocarcinoma.
But this pathogenesis presents an epidemiological puzzle. H. pylori prevalence is incredibly high globally. In many developing nations, over half the population is infected with it, yet only a tiny fraction, perhaps 1 to 3% of infected individuals ever actually develop stomach cancer. If it is a group 1 carcinogen, why doesn't everyone infected get the disease?
That paradox points directly to the incredible complexity of the microenvironment. The bacterium alone is rarely enough to complete the job. The development of cancer requires a perfect storm. The specific strain of H. pylori must possess highly virulent genes, the host's genetic immune response must lean towards severe, damaging inflammation, and crucially, it requires the presence of environmental cofactors.
Like the salt.
Exactly. High salt intake synergizes with the bacteria to worsen the damage, while diets high in fresh fruits and vegetables provide antioxidant protection. The rogue seed is the bacteria, but it absolutely requires the precise toxic soil to force the cells into malignancy.
While stomach cancer was defeated in the West by something as simple as a refrigerator changing our food storage, the cancer further down the digestive tract, colorectal cancer, is being actively fueled by the composition of the food itself. Colorectal cancer has a very high incidence in high-income regions like Australia, Europe, and North America, deeply tracking with westernization.
It's a very clear trend.
Let's unpack the pathology here because colorectal cancer is a fascinating study in observable disease progression. This is not a rogue state that materializes out of thin air overnight.
No, it has one of the clearest, most well-documented developmental timelines in all of oncology, known as the adenoma-carcinoma sequence. The vast majority of colorectal adenocarcinomas do not start as invasive cancers. They begin as benign adenomatous polyps, small, localized overgrowths of the mucosal lining.
Going back to our analogy, these polyps are the factories building unauthorized extensions. They aren't malignant yet.
Exactly, but they are genetically unstable. Over a period of typically 10 to 15 years, these benign adenomas accumulate sequential mutations, classic hits to genes like the APC tumor suppressor, then the KRAS oncogene, and finally the P53 gene driving them toward malignancy.
So it's a slow burn.
Very slow. The clinical risk of a specific polyp turning into an invasive rogue state is dictated by three primary factors observed during a colonoscopy. First, the size of the polyp, specifically if it is greater than 1 centimeter. Second, the microscopic architecture, as polyps with finger-like villous shapes are statistically more dangerous than smooth tubular ones. And third, the degree of cellular dysplasia, or how structurally chaotic the cells look under the microscope.
That 10 to 15-year temporal window, that slow, predictable march from normal mucosa to benign adenoma to invasive carcinoma, is the exact vulnerability we exploit for secondary prevention. I like to think of regular colonoscopies and fecal occult blood testing as an early warning radar system.
That's a great way to put it.
We aren't just looking for full-blown rogue states that have already invaded. We are actively searching for the rebel training camps, the adenomas. When a gastroenterologist finds a polyp during a scope and snips it out, they are literally severing the timeline. They're destroying the rebellion years before it ever has the chance to launch an attack.
It is the ultimate preventative intervention. Now, when we look at why these mutations happen in the colon, we have to carefully differentiate between rare genetic drivers and ubiquitous environmental ones. There are highly penetrant inherited genetic syndromes that guarantee cancer. For example, familial adenomatous polyposis, or FAP, involves an inherited germline mutation in the APC gene.
That's the one where they develop hundreds of polyps, right?
Yes. Patients with FAP develop hundreds, sometimes thousands, of polyps in their teens and 20s and have a near 100% risk of developing colon cancer if the colon isn't surgically removed. There is also Lynch syndrome, driven by inherited mutations in the DNA mismatch repair genes, leading to massive genomic instability.
But the textbook is very clear on the epidemiology. These highly penetrant genetic syndromes are rare. They account for a very small fraction of total global colorectal cancer cases, perhaps around 5% combined. The vast majority of cases, over 90%, are sporadic, meaning they are driven by the environment interacting with normal baseline genetics.
And the epidemiological evidence strongly points to the Western lifestyle as the dominant environmental driver. High intake of red meat and heavily processed foods provides a constant stream of mutagenic N-nitroso compounds and heme iron to the colonic mucosa. Furthermore, obesity and physical inactivity drive hyperinsulinemia, which acts as a systemic growth factor, promoting the proliferation of colonic epithelial cells.
It's basically a recipe for disaster.
Conversely, diets rich in dietary fiber accelerate transit time, reducing the time carcinogens spend in contact with the gut wall, while adequate calcium, vitamin D, and even regular aspirin use act as protective anti-inflammatory factors.
We are what we eat, and our colonic cells are the frontline soldiers dealing with the chemical fallout of our diet. Let's shift focus and unpack breast cancer. This is a monumental public health challenge. It is the most frequent cancer among women worldwide and the leading cause of cancer death among females globally. When you look at the epidemiological incidence curves comparing different regions, the data is striking.
It really is.
In high-income Western countries, the incidence rates of breast cancer skyrocket steadily after age 45, climbing higher and higher post-menopause. But in low- and middle-income countries, the curve acts completely differently. It rises during the reproductive years, but then flattens out significantly or even drops after menopause. What biological mechanism is driving that massive demographic difference?
The combined epidemiological and biological evidence strongly points to one primary macro-environmental driver: continuous, cumulative, lifetime exposure to endogenous hormones, specifically circulating estrogen and progesterone.
So it's about the hormones.
Yes. In high-income countries, the demographic and reproductive patterns have fundamentally shifted over the last century. Women in the West typically experience earlier menarche, the onset of menstruation, due to better childhood nutrition. They experience later menopause, they have fewer pregnancies overall, and they tend to have shorter cumulative durations of breastfeeding.
Why do those specific reproductive milestones matter to a breast cell?
Because every single one of those factors, earlier start, later end, fewer pregnancies, less breastfeeding, increases the total lifetime number of uninterrupted menstrual cycles a woman experiences. During every menstrual cycle, the breast tissue is bathed in estrogen and progesterone, which signal the epithelial cells to proliferate and divide in preparation for potential lactation.
Right.
Estrogen is essentially acting as a potent growth signal, fulfilling the first hallmark of cancer. More cycles mean more cellular divisions. More cellular divisions mean a mathematically higher chance of a random genetic copying error occurring.
That makes total sense.
In regions where women have later menarche, multiple pregnancies, and breastfeed for several years, those reproductive events act as prolonged pauses. They temporarily stop the ovulatory cycle and give the breast tissue a rest from the constant proliferative signaling of estrogen.
So the hormones are continuously stepping on the cellular gas pedal, driving proliferation. And this continuous exposure model ties perfectly into the genetic profile of the tumors. We all hear about the high-penetrance breast cancer genes like BRCA1, BRCA2, PTN, and TP53.
Yes, inheriting a mutation in one of those genes carries a massive, terrifying lifetime risk of developing breast and ovarian cancer. The BRCA genes are heavily involved in homologous recombination. They fix severe double-strand breaks in DNA. If they are broken from birth, the genomic instability accelerates rapidly.
It's an accelerant.
But again, just like with colon cancer, it is vital from a public health perspective to realize that these high-penetrance genes only account for approximately 2 to 5% of total breast cancer cases globally.
The overwhelming majority of familial and sporadic risk comes from complex interactions between dozens of lower penetrance genetic variations and the hormonal environmental factors we just discussed. And the textbook highlights a critical clinical nuance. Breast cancer is absolutely not a single monolithic disease. It is a family of distinct molecular subtypes, and their risk profiles differ completely based on the tumor's receptor status.
This is a vital distinction. For tumors that express estrogen receptors, ER-positive breast cancers, which rely on estrogen to grow the reproductive history factors we discussed, like nulliparity, meaning never having given birth, and late age at first birth, are very strong risk factors. Additionally, postmenopausal obesity is a major driver because after the ovaries shut down, adipose tissue becomes the primary source of estrogen synthesis in the body.
That brings us back to the adipose tissue acting as an endocrine organ.
Exactly. Furthermore, alcohol consumption is a consistent risk factor, likely because it impairs the liver's ability to clear circulating estrogen.
But the textbook notes that for triple-negative breast cancers, tumors that lack estrogen, progesterone, and HER2 receptors, the risk profile is entirely different, almost inverted in some aspect.
It is a profound paradox. Because triple-negative tumors do not rely on estrogen for growth, they aren't driven by the same cumulative exposure model. In fact, high parity having multiple births, which protects against ER-positive cancer, is actually associated with an increased relative risk for developing triple-negative breast cancer in some populations.
Wow, that's wild.
Furthermore, some cohort studies have found that moderate alcohol consumption might surprisingly have a slight protective association against triple-negative subtypes, though the mechanisms are highly complex and definitely not a basis for clinical recommendation.
It perfectly emphasizes that the rogue state adapts to the specific conditions of its host environment. Different soil breeds a different type of rebel. Let's move back to the gastrointestinal tract and look at esophageal cancer. For anyone studying for board exams or pathology rotations, this organ is a classic high-yield scenario because it presents a beautiful dichotomy framework. We have two distinct microscopic histologies driven by two completely different sets of risk factors and demographics existing in different parts of the same 6-inch tube. Let's break them down.
The first subtype is squamous cell carcinoma, or SQCC. This typically arises in the upper and middle thirds of the esophagus, which is naturally lined with flat squamous cells designed to handle the friction of swallowing food. Geographically, we see incredibly high epidemic rates in what epidemiologists call the esophageal cancer belt, a geographic band stretching from northern Iran through the Central Asian republics and into northern and central China.
When I was first reading the epidemiological data on that Asian cancer belt, I automatically assumed it was driven by a massive spike in tobacco use. But the data points to something entirely different causing the damage in that specific region.
While in Western populations, esophageal squamous cell carcinoma is overwhelmingly driven by the synergistic, multiplicative combination of heavy tobacco smoking and heavy alcohol drinking, the drivers in the Asian belt are different. The epidemiology points heavily to thermal and physical trauma.
Thermal trauma.
Yes. It is driven by the cultural practice of drinking extremely hot tea and beverages, which physically burn and traumatize the squamous mucosa daily. This is combined with poor nutritional status, a lack of protective fresh fruits and vegetables, and the widespread chewing of areca nut and betel quid, which leach highly carcinogenic nitrosamines directly into the saliva that is then swallowed.
So squamous cell carcinoma is a disease of direct chemical, toxic, and thermal trauma burning the upper squamous lining. What about the second type?
The second subtype is esophageal adenocarcinoma. This occurs almost exclusively in the lower third of the esophagus, near the junction with the stomach. The global incidence of this specific type has sharply and alarmingly increased over the last 4 decades in high-income Western countries, primarily affecting white males.
Why the sudden demographic-specific spike in the West? What changed the environment at the bottom of the esophagus?
The spike is entirely tied to the rising macroepidemic of obesity and its mechanical consequences, specifically gastroesophageal reflux disease, or GERD. Central abdominal obesity drastically increases intra-abdominal pressure. This pressure forces the acidic contents of the stomach back up through the sphincter and into the lower esophagus.
And the squamous cells lining the esophagus are not biologically designed to handle stomach acid. They get burned.
Exactly. The chronic acid reflux constantly bathes the lower esophagus in a highly acidic inflammatory soup. The delicate squamous tissue cannot survive it. So through a remarkable feat of biological adaptation, the tissue undergoes metaplasia. It literally shapeshifts.
It changes its identity.
Yes. It swaps out its identity, replacing the squamous cells with tough, acid-resistant columnar epithelium that looks just like the lining of the intestines. This metaplastic adaptation is called Barrett's esophagus.
It is the tissue trying to survive a hostile environment.
It is a survival mechanism, yes. But that constant cellular turnover, the chronic inflammation from the acid, and the genetic instability inherent in forcing cells to change their identity create the perfect chaotic environment for dysplasia to take hold. Eventually, those metaplastic glands accumulate mutations and become an invasive adenocarcinoma.
This organ perfectly, elegantly illustrates how different environmental exposures physically shape the microscopic pathology of a disease. Boiling hot tea, areca nuts, and cigarette smoke physically burn the top half of the tube, resulting in squamous cell carcinoma. Meanwhile, obesity-driven mechanical pressure and chronic acid reflux burn the bottom half of the tube, forcing metaplasia and resulting in adenocarcinoma. It is a profound example of macro-environmental changes dictating the microenvironmental outcome.
That's a great summary.
Let's quickly touch on a few other highly lethal cancers covered in the textbook, starting with pancreatic cancer. It is often referred to in clinical circles as the silent killer. The incidence is rising in developed regions, and the prognosis remains notoriously grim, with a median 5-year survival rate hovering around a dismal 5%. Why is this specific rogue state so invariably deadly?
The lethality of pancreatic cancer is primarily due to its anatomical location and its microenvironment. The pancreas sits deep in the retroperitoneal space of the abdomen. Therefore, tumors can grow quite large and establish distant metastatic colonies. The rogue state fully expands long before they compress any surrounding structures to cause noticeable early symptoms like jaundice, back pain, or sudden weight loss.
So it hides.
It hides very well. By the time a patient feels something is wrong, the cancer is usually widely disseminated. Furthermore, pancreatic tumors are notoriously desmoplastic. They surround themselves with a dense fibrous scar tissue stroma that physically prevents chemotherapy drugs from penetrating the tumor bed.
It builds its own fortress. And what are the known hazards supplying this fortress?
The most firmly established risk factor is, again, tobacco smoking, which accounts for roughly 20 to 30% of all cases. Beyond tobacco, a history of chronic pancreatitis, often driven by heavy alcohol use and long-standing type 2 diabetes, are significant risk factors, both contributing to a local environment of chronic inflammation and abnormal insulin signaling.
Then we have head and neck cancers, encompassing the oral cavity, pharynx, and larynx. Again, because these tissues are exposed to the outside world, we see squamous cell carcinomas completely dominating the histology here. The risk factors largely mirror the upper esophageal SQCC. We just discussed the synergistic devastation of smoking and alcohol, but the textbook points out unique, fascinating regional variations.
Yes. In India and parts of South Asia, the localized chewing of tobacco and areca nut mixtures are massive dominant drivers for oral cavity cancers, specifically on the buccal mucosa, where the quid is held against the cheek for hours. And crucially, just as we saw with cervical cancer, the epidemiology of head and neck cancer in the West has undergone a viral paradigm shift.
The HPV shift.
Exactly. Human papillomavirus, specifically the HPV-16 strain, has emerged as a major driving cause for oropharyngeal cancers of the tonsils and base of the tongue in Europe and North America. This viral driver has fundamentally changed the demographics, often affecting younger patients without significant smoking or alcohol histories.
And for cancers of the larynx, the voice box, the text notes an interesting anatomical split in risk factors. Tobacco smoking is a much stronger driver for glottic tumors, those occurring directly on the vocal cords themselves. However, heavy alcohol consumption is a stronger independent driver for supraglottic tumors, located in the tissues just above the cords. Plus, the larynx is highly susceptible to occupational hazards, like chronic inhalation of asbestos fibers or strong inorganic acid mists, like sulfuric acid in industrial settings.
Which highlights a core tenet of public health. Industrial regulation, ensuring proper ventilation, and enforcing occupational health standards are literally forms of primary cancer prevention. Protecting the worker protects the genome.
Let's tackle prostate cancer next. This represents a fascinating, controversial public health story regarding how we define and measure disease. Prostate cancer has a very high reported incidence in developed nations like the US, Australia, and Western Europe, and is a leading cause of cancer death in men. But the text makes it abundantly clear that this high recorded incidence is deeply, inextricably tied to the adoption of a specific medical intervention, the widespread use of the PSA, or prostate-specific antigen, blood test for screening.
That is correct. When PSA testing became widely available and aggressively adopted in the late 1980s and 1990s, the epidemiological incidence curves for prostate cancer artificially skyrocketed. Millions of men had their blood drawn, elevated PSA levels were found, biopsies were performed, and we were suddenly diagnosing thousands upon thousands of early-stage microscopic cancers that previously would have gone completely unnoticed.
And here is my pushback. And I know trainees in the public struggle deeply with this conceptual paradox. If we have a simple, relatively inexpensive blood test that successfully detects cancer early, why did major public health bodies like the U.S. Preventive Services Task Force, the USPSTF, historically give routine PSA screening for healthy asymptomatic men a grade D? Why do they explicitly controversially recommend against actively looking for the rogue state? Shouldn't finding cancer early always be the goal?
That assumption that finding disease early is inherently and always good is the great fallacy of screening. The prostate cancer story is a masterclass in public health ethics and the vital necessity of understanding overdiagnosis bias. The biological reality is that prostate cancer is incredibly heterogeneous, but a vast proportion of these tumors are extraordinarily slow growing.
So they aren't all immediate threats.
Right. Autopsy studies show that a huge percentage of men in their 70s and 80s who died of heart attacks or strokes had microscopic prostate cancer, and they never knew it. They died with prostate cancer, not of it. The rogue state was so indolent, so lazy, it was never going to launch an attack.
The PSA test is highly sensitive. It acts like a massive dragnet. It finds a lot of cancer. But the critical flaw is that the blood test cannot reliably, easily differentiate between a highly aggressive, rapidly lethal rogue state and a tiny, indolent, lazy rebellion that would have never caused the patient a single day of harm in their natural lifetime.
And that inability to differentiate is where the catastrophic harm occurs. If you screen and diagnose a healthy 75-year-old man with a slow-growing, indolent prostate cancer, the psychological terror of the cancer label is immediate and immense. Driven by that fear, he undergoes severe treatments, radical prostatectomy surgery to remove the gland, or intensive pelvic radiation.
They have huge side effects.
Those treatments carry severe, life-altering, guaranteed risks of permanent urinary incontinence, impotence, and severe bowel dysfunction.
So by finding a disease that was never going to hurt him, our intervention actually destroyed his quality of life.
Precisely. The USPSTF looked at the massive population data and determined that the severe guaranteed harms of treating hundreds of thousands of indolent cancers across the population mathematically and ethically outweighed the marginal statistical benefits of catching the few aggressive ones early. You are essentially carpet bombing the village to save it from a threat that might never have materialized.
That is such a vital, humbling concept for clinicians to grasp. Finding disease does not automatically equal improving health. Sometimes the pursuit of the rogue cell causes more systemic damage than the cell itself. Okay, our final specific organ system in our deep dive is cervical cancer. This disease is a stark representation of profound global health inequity. It is devastating in low-resource settings, ranking as the third leading cause of cancer death among women in developing regions, yet it is highly controlled in high-income nations.
And biologically, it is unique because it has a single definitive necessary cause persistent long-term infection with high-risk oncogenic strains of the human papillomavirus, predominantly types 16 and 18.
And how does that pathogenesis work?
The pathogenesis is highly localized and sequential. The virus specifically targets and infects the transformation zone of the cervix, the exact anatomical boundary where the protective squamous cells of the outer cervix meet the glandular columnar cells of the inner canal. Over a period of years or decades, the viral proteins directly bind to and degrade the host cells p53 and Rb tumor suppressor proteins.
They cut the brakes.
Right. Without those breaks, the tissue is driven from normal to mild cervical intraepithelial neoplasia, CIN1, progressing to severe dysplasia, CIN3, and finally breaking through the basement membrane as invasive squamous cell carcinoma.
This clear, observable, stepwise pathogenesis occurring over years, combined with a single known infectious viral cause, makes cervical cancer the ultimate shining triumph of both primary and secondary public health prevention. It is a disease we can theoretically eradicate.
For secondary prevention catching the disease before it turns invasive, we have the traditional Pap smear. We scrape cells from that transformation zone, look at them under a microscope, and identify those precancerous dysplastic CIN lesions. If we find them, we simply freeze them off or excise them locally. We remove the rebel training camp before it mobilizes.
But the textbook highlights a crucial adaptation for global health. In low-resource settings, establishing a massive infrastructure of laboratories and highly trained cytopathologists to read millions of Pap smears is economically impossible. So, public health adapted.
They did. They utilize visual inspection with acetic acid, or VIA. A trained nurse applies a simple, cheap vinegar solution directly to the cervix. Any precancerous dysplastic lesions instantly turn stark white and can be frozen off in the exact same clinic visit. It is immediate, inexpensive, and highly effective for the environment. Furthermore, the global standard is now rapidly shifting toward primary HPV DNA testing swabbing to detect the presence of the high-risk viral hazard itself, rather than waiting to see the cellular damage it causes.
But the absolute holy grail of oncology is primary prevention, stopping the rogue state from ever acquiring its first mutation. And we achieve that with the HPV vaccines. By vaccinating pre-adolescent girls and boys against the major oncogenic strains of the virus before they ever become sexually active and exposed, we are effectively armoring the cells. We are cutting off the rogue state's primary viral accelerant before it can even initiate the first step of the cascade. It is, without hyperbole, one of the greatest public health achievements of our lifetime.
It truly is. We are engineering a future where cervical cancer could be a historical footnote, which provides a perfect, logical bridge to our final major conceptual topic of the day. We have toured the global epidemiology and the specific pathology of these diverse organ systems. Now let's pull all of these threads together and codify the overarching rules of engagement. Let's look at the principles of primary and secondary prevention.
Let's start with primary prevention, stopping cancer from occurring in the first place. The expert consensus in public health utilizes a classic multi-stage model of carcinogenesis initiation, promotion, and progression. How does breaking it down to these three phases guide our public health interventions?
It provides distinct targets for policy. Initiation is the first step. It is the rapid, irreversible genetic mutation caused by an initial carcinogen, a chemical adduct binding to DNA, or a viral insertion. Primary prevention at this stage aims to eliminate the mutagen entirely. Banning asbestos, regulating aflatoxin in crops, and administering the HPV vaccine are all interventions aimed at stopping initiation.
But as we discussed, one initiated mutated cell usually isn't enough to cause cancer. It needs to multiply.
That brings us to promotion. Promotion is the long, reversible process that stimulates those initially mutated initiated cells to divide and form a pre-neoplastic mass. Promoters are not necessarily mutagens themselves, they are growth signals. This is where chronic inflammation, obesity, and circulating hormones like excess estrogen play a massive role.
They fertilize the soil.
Exactly. Primary prevention here aims to alter the host environment to starve the initiated cells. Interventions include public health campaigns for weight loss, which reduces circulating inflammatory cytokines and estrogen levels, effectively removing the promotion signals.
And progression is the final, deadly phase, where the growing mass acquires further mutations, becomes genetically chaotic, and gains the invasive characteristics of the 6 hallmarks to metastasize. When we talk about stopping exposure during these phases, we must return to a vital mathematical reality in the text that we touched on earlier regarding lung cancer and tobacco. It is the crucial difference between the dose rate and the duration of exposure.
This is perhaps the most critical mathematical concept for a public health trainee to grasp. In models of lung cancer, the incidence rate increases with the first or second power of the daily dose, how many cigarettes you smoke a day. If you double your daily dose, your risk roughly doubles or quadruples, but the risk increases with the fourth power of the duration, how many years you have been continuously smoking.
The fourth power. That exponent changes everything. To make the math concrete, if two people smoke the exact same total lifetime number of cigarettes, but person A smokes 20 a day for 20 years and person B smokes 10 a day for 40 years, their risk is not the same. Person B's risk is exponentially higher because the duration of time the tissue spent in a chronic inflammatory mutated state was twice as long. The mutations have decades to compound like terrible interest. Time is the true enemy.
Exactly. This mathematical reality dictates tobacco policy. This is precisely why massive public health campaigns, taxation policies, and advertising bans focus so heavily, relentlessly on preventing youth initiation. If a policy can delay a teenager from starting to smoke from age 15 to age 25, you drastically mathematically reduce that exponent over their lifetime, saving millions of lives even if they eventually start.
Now, let's talk about the rules of secondary prevention screening. We've used the early warning radar metaphor, and it sounds great in theory. Catch it early, save a life. But the textbook lays out the holy trinity of screening biases. These are the epidemiological traps, the statistical illusions that can make a screening program look wildly successful on paper, even when it is completely failing to save a single life. Let's break them down carefully. First is lead time bias.
Lead time bias is a devastating illusion. It occurs when a screening test simply advances the calendar time of diagnosis without actually altering the biological course of the disease or extending the patient's true lifespan.
Can you give an example?
Sure. Imagine a hypothetical patient who develops a microscopic tumor at age 60. This specific tumor is destined to grow and eventually kill them at age 70. Without any screening program, the tumor grows silently until it causes pain or symptoms. The patient goes to the doctor, is diagnosed at age 68, and dies at 70. They live 2 years with the knowledge of their diagnosis.
Okay, now let's introduce a screening program. We implement a new, highly sensitive screening scan. We scan that same patient at age 65. We find the microscopic tumor early. We treat it, but because the biology of that specific cancer was inherently lethal and resistant to therapy, the patient still dies at age 70.
Right, and look at what happens to the statistics. In the unscreened scenario, the survival time from diagnosis was 2 years. In the screened scenario, the survival time from diagnosis was 5 years. The screening advocates will point to the data and shout, "Our new scan more than doubled survival time. It jumped from 2 to 5 years."
But the patient didn't live a single day longer. They still died at exactly 70. All the screening program achieved was making the patient live 3 extra years with the agonizing knowledge that they had cancer and subjecting them to 3 extra years of toxic treatments. The extended survival time was a mathematical artifact of lead time bias.
Precisely. To prove a screening test actually works, you cannot look at survival time from diagnosis. You must look at overall disease-specific mortality in randomized controlled trials to see if fewer people are actually dying of the disease. The second major trap is length bias. This happens because screening programs are episodic. They occur periodically, say, every 2 years. Because of this interval, the screening test is mathematically much more likely to detect slow-growing, indolent tumors that spend years in the detectable preclinical phase.
My favorite analogy for this is taking a photograph of a busy highway exactly once an hour. When you look at your photos, what do you capture? You're going to capture hundreds of photos of slow-moving tractors that take hours to travel the single mile. But you're going to capture very few photos of the speeding sports cars rocketing down the highway at 150 miles an hour. They slip right through the 1-hour interval between your snapshots.
The biology acts exactly the same way. Highly aggressive, fast-growing tumors, the sports cars often develop and kill the patient rapidly in the interval between scheduled screenings. Therefore, the cohort of patients whose cancers are detected by the screening program is disproportionately filled with people who have slow-growing, less dangerous tumors, the tractors. When you look at the survival rates of your screened cohort, it looks fantastic. But it isn't because the screening saved them, it is because the screening test preferentially selected for the least dangerous cancers. That is length bias.
And the third bias in the trinity is the one we explored deeply with prostate cancer. Overdiagnosis bias. This is the extreme endpoint of length bias. It is detecting microscopic lesions that meet the strict morphological, pathological definition of cancer under a microscope. But biologically, they are so slow-growing they would have never progressed to cause clinical disease or death in the patient's remaining lifetime.
Detecting and treating these harmless lesions causes massive iatrogenic harm, surgical complications, radiation toxicity, profound psychological distress, with zero possibility of benefit because the patient was never going to die from that specific cluster of cells anyway. It is the ultimate cautionary tale of modern medical technology outpacing our understanding of tumor biology.
To bring all of these complex molecular mechanisms, epidemiological data points, and screening biases into actionable reality, the text summarizes the global consensus into the European Code Against Cancer. It serves as the ultimate evidence-based public health checklist for minimizing the risk of the rogue state.
It is elegant in its simplicity, but powerful because of the massive data backing every single point. Do not smoke and make your home smoke-free. Take action to maintain a healthy body weight. Be physically active in everyday life. Eat a diet rich in whole grains, pulses, vegetables, and fruits, while severely limiting high-calorie foods, sugary drinks, red meat, and processed meats. Avoid alcohol. Avoid excessive sun exposure, especially for children. Protect yourself against cancer-causing substances in the workplace by following occupational health and safety instructions. Ensure your children participate in vaccination programs for hepatitis B and HPV. And finally, participate in organized, quality-controlled, evidence-based screening programs for bowel, breast, and cervical cancers.
It sounds like basic, almost folksy advice you've heard a million times. But as we have rigorously explored today, every single one of those seemingly simple bullet points is backed by a massive, complex network of epidemiological data and intricate biochemical mechanisms, all aimed at denying the rogue cellular state the accelerants, the growth signals, and the chaotic environment it absolutely needs to thrive. Which brings us to the end of our deep dive through the frameworks of Chapter 8.2. We have covered an immense amount of ground today. We traveled from the microscopic hallmarks of a single mutating cell through the vast global epidemiology of the master environmental risk factors down into the specific divergent pathologies of major organ systems, and finally navigated the treacherous statistical biases of how we measure our public health successes and failures. But I want to leave you, the listener, with a final provocative thought to mull over as you close your books today. We currently spend billions upon billions of dollars searching for molecular cures to cancer. We decide incredibly complex, brilliantly engineered targeted therapies to fix one specific broken protein, to block one specific receptor in a mutant cell. We are obsessed with the seed. Yet, as we've seen unequivocally today, the most profound, world-changing reductions in global cancer mortality haven't come from a test tube or a targeted biologic. They have come from the invention of the kitchen refrigerator. They have come from aggressive taxation on tobacco products. They have come from clean water, better crop storage, and the deployment of childhood vaccines. As you move forward in your clinical or public health career, the next time you look at the patient in front of you or the community data set on your screen, ask yourself a fundamental question. Are you only trying to treat the mutant cell, or are you also working to treat the environment that allowed it to rebel in the first place?
A vital, necessary perspective for the future of global health.
All right, let's reinforce what we've learned and cement these frameworks. It is time for the rapid-fire single best answer recall prompts. I will read the question, we will pause briefly for you to think of the answer, and then we will provide the correct response and the explanation. Question 1. Which screening bias refers to the epidemiological phenomenon where a periodic screening test disproportionately detects slowly progressing, less aggressive tumors, making the screening program's survival statistics look artificially successful? Take a second to lock in your answer.
The answer is length bias. Because highly aggressive, fast-growing tumors have a very short asymptomatic preclinical phase, they often arise and cause symptoms in the interval between screenings. Therefore, they are less likely to be caught during periodic screening compared to slow-growing, indolent tumors that spend years in the detectable phase. For review, refer to the section on principles of primary and secondary cancer prevention.
Question 2. While many infectious agents act as cofactors, which specific infectious agent has an attributable fraction of essentially 100% for the development of cervical cancer? Got your answer.
The answer is high-risk strains of the human papillomavirus, or HPV, predominantly types 16 and 18. Persistent infection with these oncogenic strains is considered a necessary biological cause for the development of cervical carcinoma. For review, refer to the section on etiological risk factors in cervical cancer.
Question 3. A concerning rise in the incidence of hepatocellular carcinoma is being observed in high-income Western nations. In the absence of endemic viral hepatitis B or C, or heavy alcohol-induced cirrhosis, this rise is most strongly and mechanistically associated with which underlying metabolic condition? Think about it for a beat.
The answer is non-alcoholic fatty liver disease, or NAFD, which is intrinsically driven by the epidemics of obesity, insulin resistance, and metabolic syndrome. Crucially, NAFLD can increase the risk of hepatocellular carcinoma even before the liver has developed full end-stage cirrhosis. For review, refer to the section on cancer of the liver.
Question 4. What is the predominant histological subtype of esophageal cancer found in the high-incidence regions like northern Iran and central China? And what are the primary macroenvironmental risk factors driving it in those specific regions? Take a second.
The answer is squamous cell carcinoma. While driven by smoking and alcohol in the West, in these specific high-risk Asian regions, the main drivers are thermal trauma from drinking extremely hot beverages, poor nutritional status, and the chewing of areca nut and betel quid. For review, refer to the section on cancer of the esophagus.
Question 5. According to the mathematical principles within the multi-stage model of carcinogenesis, what is the specific relationship between tobacco smoking and lung cancer risk regarding the dose rate versus the duration of exposure? Think about the math here.
The answer is that the risk of lung cancer depends much more heavily on the duration of exposure increasing to the fourth power of time than on the daily dose rate, which only increases to the first or second power. The compounding nature of time is the dominant mathematical factor in carcinogenesis. For review, refer to the section on principles of primary and secondary cancer prevention.
Excellent work. Keep building those frameworks and keep thinking structurally. Here are the details of this episode.
Cancer. Episode description. Cancer is not a single disease, but a family of disorders defined by uncontrolled cellular growth, genomic instability, and progressive invasion. It is both biological inevitability and environmental consequence shaped by aging, exposure, behavior, and inequity. In this episode of Medlock Holmes, Global Public Health, Holmes examines the epidemiological and structural dimensions of cancer as a global health challenge.
The global burden and rising incidence. The epidemiological transition and aging populations. Major cancers worldwide: lung, breast, colorectal, prostate, liver, cervical. Behavioral risk factors: tobacco, alcohol, diet, physical inactivity. Infectious causes: HPV, HCV. Environmental and occupational carcinogens. Screening and early detection strategies. Vaccination as cancer prevention. Palliative care and survivorship. Cancer reveals the interface between molecular mutation and societal structure. Tobacco policy, vaccination coverage, occupational regulation, and screening infrastructure all shape cancer incidence and mortality. Holmes traces how prevention, early detection, and system design determine whether cancer becomes a death sentence or a chronic condition. The investigation is not into rogue cells alone, but into the environments that permit them to thrive.